guys, so today we're looking at exercise 11.3. This is question 8 on proofs involving divisibility. Prove by induction that 2 to the power of 3n minus 1 is divisible by 7. So in this case, we want to prove that our statement is divisible by 7 for all cases of n. So let's just call our general statement f of n. So f of n is equal to 2 to the power of 3n minus 1. So we want to prove that this is true when n is equal to 1. So we substitute in 1 and we get 2 to the power of 3 minus 1, which is equal to 8 minus 1, which gives us 7. 7 is divisible by 7, therefore this statement is true when n is equal to 1. In step 2, we have to assume that our proposition or our general statement is now true when n is equal to any value k. So we assume that this is true, that f of k, which is 2 to the power of 3k minus 1, we assume that this is true. So we assume that this statement is divisible by 7. And in step 3 now, we have to prove that our proposition is true when n is equal to k plus 1, given that it is true when n is equal to k. So what we have to do here is directly write f of k plus 1 in the form of f of k and some remainder. We will know then that f of k is divisible by 7 because it is assumed in step 2. And then we take a remainder and we write it as a factor of 7, therefore proving this is also divisible by 7. And so any value k plus 1 is also divisible by 7. Okay, so let's have a look at what we mean. So we want to show that f of k plus 1 is divisible by 7. So we're going to substitute in k plus 1 for n in our general statement. This gives us 2 to the power of 3 times k plus 1 minus 1. So we want to show that this general statement is divisible by 7. So the first thing we're going to do here is use our indices rules to simplify this exponent. So we know that a to the power of n times n will give us 2 to the power of 3k plus 3. So I'm just multiplying in my 3, expanding out my brackets. And using our exponent rules, a to the power of n plus m can be written as a to the power of n times that same base to the power of your second exponent, which means that this can be written as 2 to the power of 3k times 2 to the power of 3 minus 1. Simplifying this, we get 2 to the power of 3k times 8 minus 1, which gives us 8 times 2 to the power of 3k minus 1. We now want to split this term so we can write our f of k plus 1 in the form of f of k and some remainder. So this is the same as writing 7 to the power of 7 times 2 to the power of 3k plus 2 to the power of 3k minus 1. So if you have 8 2 to the power of 3k's, you can split this into 7 2 to the power of 3k's plus 1 2 to the power of 3k's. And from here, let's just give ourselves a bit more room. And from here, we can see that this term can be written as f of k. So we have 7 to the power times 2 to the power of 3k plus f of k. Now we know that f of k is divisible by 7 because we proved it in step 2. And 7 times 2 to the power of 3k is also divisible by 7. So our value here, our multiple, is divisible by 7. And therefore, our statement is true when n is equal to k plus 1. So our conclusion is that our proposition is true when n is equal to 1. It's true when n is equal to k, and also true when n is equal to k plus 1. Therefore, by induction, it is true for all values of n which are elements of our natural number.